So we spent a lot of time talking about moments and equivalent forces, force resultants, resultant moments, all of this. And this was all building up to this idea of equilibrium of a body, right? So we've done equilibrium of a particle before, right? That was where we had, a point or something representative of a point in space, maybe in 3D, where we were saying, all right, the sum of all my forces in the x direction, the y direction, and the z direction, those are all going to be 0. That was equilibrium of a particle. Now, we're going to be looking at bodies, right? So these are things that are a little bit too complex to be represented as just a particle. So maybe a bridge, for example. You might represent a bridge as the body itself. It would be oversimplifying too much to just say it's one singular point. You can have multiple forces acting in different spots along a bridge. So instead we have this equilibrium of a body, of a rigid body. This is where we usually represent something. Could be even an airplane, maybe, right? An airplane. And we say, okay, we have all these forces on the airplane. Let's simplify that, do our equilibrium equations for a rigid body. And these require us to know about moments. Our equilibrium equations for a body are going to be still that the sum of our forces is 0. So our some of our y forces, our x forces, those are still 0. Typically it's x and y. It's not as common that we see the z, but we can. And that the sum of our moments is 0. This is really a critical part of our equilibrium of rigid bodies. So to work with these bodies, there are a couple things we need to go over, which is one, how to draw these for a body rather than for a particle, because we do draw them a little bit differently. And then two is to introduce this idea of support reactions. So when we have something like a bridge, something like a beam, these things are supported, right? They're not just floating in space. Like sometimes our particles were just floating in space, right? If you have a knot in a string or something like that, our equilibrium of a particle was often just floating in space. But now we have this idea of support reaction, where when you are acting on something is acting back up, right? The normal force that something is experiencing. So the most common ones that we see of this are, if I have this as my portion of a beam, we have something called a pinned reaction. And what a pinned reaction is it looks something like this. We usually represent it in a quick drawing as just a triangle. And what it does is it locks in the x and y movement. So it can't move in the x direction, it can't move up and down in the y direction, but it can rotate, right? So you can think of something like a wheel, right? Your bike axle locks in your wheel so that it can rotate around that point, but it doesn't move in the x and y or y directions. So this is a pinned connection. And the reactions that we see on this, since our x and y are fixed, is we see a y reaction acting kind of like a normal force pushing up on the beam. And we also see an x reaction, right, from being held in place. These are the two reactions that we see on a pinned connection. Another super common one that we see is called a roller. And it's usually represented by a circle because it allows freedom of movement in the x direction. This is very common in real life in something like a bridge, right? If you ever drive across a bridge or walk across a bridge and you notice that it has these metal teeth that kind of intersect, but they're not always touching. It's because it gives the bridge room to breathe and expand, right? There is thermal deformation of a bridge. When it gets really hot, it will expand. When it gets cold, it contracts. And so the bridge needs room to move and stretch. And especially with loading, right? If there are a lot of cars on the bridge, then there's more compression happening on the concrete of the bridge. And if there are less cars, then there's a little less compression. So it needs this room to move around. Otherwise, our bridges would constantly be breaking because they're constantly under changing loads. So we have them on rollers. Some portions are fixed, some portions are pinned, some are on rollers, so that it allows this freedom of deformation. The bridge has the ability to move a little bit so that it doesn't just break. So this is a roller connection. We could call this a roller. And the reaction that we see here is only the Y force, right? It's not fixed in any way. We only see the normal force from the roller acting up on the beam. And then finally, we have what we call a fixed connection. So this is something usually like a wall, where something is firmly bolted into the wall, fixed support. Maybe you've concreted it into the ground where it can't move at all, right? There is mobility is completely restricted. So not only do we have a Y reaction and an X reaction, but we also have a moment reaction. Because it's prevented from rotating, there is a counter moment. If anything tries to rotate it, there is a moment from the fixed reaction here that prevents it from rotating. So these are the main support reactions we see for bodies. There are several other ones. There's a full table in your book. It looks something like this that tells you all sorts of different ones. There are rockers, there are frictionless surfaces, there are other forms of fixed members and hinges and lots of different options. But the ones here are the three most common ones that you're going to come across. So we include these in our free body diagrams when we're drawing these for our rigid bodies. So this video is just going to be examples of how we set up these free body diagrams, being sure to include all of the forces, simplifying and writing down our distributed loads, and what a free body diagram for a body looks like. Include these support reactions. What do these free body diagrams look like before we actually get into solving these equilibrium equations? So let's take a look at how we draw these free body diagrams. In this example, we're just given a simple beam and it only has one single applied force on it. It has one 1200 Newton force acting on it, and it has a fixed connection on the left-hand side, right? It's attached to a wall. So if I want to draw the free body diagram for this, what I always do is draw the outline of the body. So regardless of the shape, whether it's rectangular or a plane or, whatever kind of shape it is, draw the basic outline of the shape. So here, I'll go ahead and represent it as a rectangle. You can also represent it as a straight line. That's also acceptable, but sometimes it's a little easier if the geometry is really complicated to kind of leave it as the shape that it is. Right, so now I'm just going to go in and I'm going to add all of my forces. So of course I have this 1200 Newton applied force here. And now I want to make sure I capture my support reaction forces. So I have a force in the Y direction, a force in the X direction, and a moment, all on this free body diagram because it's a fixed connection on the left-hand side. Now, you can also choose to put in the dimensions here, the 2 meters and 4 meters, which I do recommend because if you're taking moments, it's a lot easier to refer to your diagram that you're drawing than trying to backtrack where all of these directions are coming from. So this would be the complete full body diagram for our shape on top. Let's try another one. In this example, we can see that we now have 3 applied forces and that our support reactions are different. So our support reaction at A is a roller and our support reaction at B is a pin. So if I draw my body here, I see that I have these applied forces. I have this 600 newtons acting at a 45-degree angle. I have this 100 newtons acting downwards, and this 200 newtons acting downwards at B. Now, notice that I didn't draw the 100 newtons, the 200 newtons, either facing in towards the beam or out towards the beam like we do for a particle, right? For a particle, we always draw it with the arrows pointing outwards from the particle. But for a body, that doesn't really matter as much. You can draw it in whatever way makes the most sense to you. You can draw it exactly how it's given to you. That's 100% okay. Right? It's just a matter of making sure all of the forces are there. Put them on the body. That's all that's important. Being important, let's do those reaction forces, right? So we said A was a roller, and a roller only has one reaction force in the vertical direction, right? In the Y direction. So here I'm going to call this AY, right? It's the A at point A. It is the force at point A in the Y direction. And I'm going to use the same kind of naming convention for B. I'm going to call this at point B, the force at point B in the Y direction. Right? Instead of calling it F, Fy, anything like that, I'll just call it the point that it's at. Right? This is a common naming convention that we see. But name things in a way that makes sense to you, right? Make sure that you're saying that this is in the Y direction. Again, B is a pinned connection, so it also has an X component, right? Bx. So just make sure that you're very clear on where these things are acting, what kind of connections you have, what kind of support reactions those have, and how does that change the way your diagram looks, right? So the major change is really just adding in those support reactions. But you may also have to do something like simplifying loading, right? So let's take a look at an example like that. So in this example, I have a distributed load across this beam with a fixed connection at point A, right? It's connected to a wall here. So I'm going to draw this, instead of drawing exactly this curved shape, I'm going to keep it as a simplified rectangle, though you can also draw it as the more accurate kind of curve shape that it is. There we go. So I've just kind of simplified it as a bar here, and what we want to do is we want to simplify the distributed loading, right? So what I'm going to do is I'm going to say, okay, I'm going to cut it off here, right? Where between my rectangle and my triangle, and I'm going to make this into just point sources. So I'm going to say, it's also convention, I would say, to have kind of like this dotted outline of where the distributed force was. But I don't believe it's mandatory. This is not something you have to have. But you want to simplify these into just point force reactions, right? So I would take my 0.5 times 6 meters, and I'll get 3 kilonewtons as an equivalent force for just this rectangular portion of the distributed loading. Right? And then this acts 3 meters inwards. And then it's another 3 meters to the triangle. And then I have my 1/2 base times height to get my distributed loading for the triangle. So 1/2 times 1/2 times 3. So I will get a resultant here that is 0.75 kilonewtons. and that acts 1/3 of the way into the triangle, so 1/3 of 3 is going to be 1 meter, and then to the end is 2 meters. And I have another reaction here at the end, 3 kilonewtons. And then I also have this moment acting at the end here, 5 kilonewton meters. So that goes on my free body diagram as well. Now the only thing I'm missing are those support reactions at A, right? Since this is a fixed reaction, I have a Y component, an X component, and a moment. So that's it for this one. That's the full free body diagram for this one. Let's take a look at one more that might not be as clear, but does illustrate some of the other things we might run into. All right, so in this final example, we have a man who's standing on this board, and he has this board that is touching these frictionless surfaces at points A and B, but that is also tethered to the wall using this yellow cord just above point B. So if I were to draw the free body diagram for this, the thing of interest here, although it seems like it could be the man, is the board that he's standing on, right? So if I draw the board that he's standing on, I want to keep the angle with it, the angle that that board is experiencing. And then I want to break down everything that I'm seeing here, right? So the first one that I think is most obvious is that there is a man on the board, right? And that man has a weight. He is enacting a force on that board, right? So he is enacting a weight here on the board. I'm just going to label it W because that's the thing that makes the most sense. As long as you make sure that all of these forces have labels, whether they're numbers or whether they're names, all of the forces need to have these labels. So we have our man's weight on here. Then we have our quote-unquote reactions at A and B. And these are really normal forces, right? These are just the walls pressing up against the board. So at A, we have this normal force at point A from the floor pushing up against the board. And then at B, we also have a normal force, but notice that the wall is slanted. So the way that it's interacting is actually at a slant, the normal force of B, right? Slanted by these angles. I have my normal force at A, my normal force at B, and then the only other thing causing a force on the board here is this tether, this yellow tether, is actually causing a tension force up the wall. Now, it might be helpful here to go ahead and include those angles. Include this angle theta, the angle phi in here, to help you kind of break down this into X and Y components as you're working through the equilibrium equations. But this is a totally acceptable free body diagram, right? It has all of the forces on it labeled, and that's what's most important. No distances were given, so no distances are listed. But these are the free body diagrams. These are how we set these up, and they'll be very important for us to actually solve these equilibrium problems. So in the next video, we're going to get into actually solving the problem.